All right, hello everyone. Welcome to AP review number 9. We're going to be talking about anti-derivatives and integration techniques, really focusing on integration techniques. Because the test this year will be open notes, I'm less concerned about you remembering every antiderivative, like the antiderivative 1 over x squared plus 1 is arctangent of x and things like that. But that is important to have filed away. We're going to focus on the actual antiderivative and integration techniques, okay? And this is really meant just to be an overview. I'm going to just really put the ball in your court on this one and ask you to be really, really self-disciplined about if some of these techniques are things that you know you struggle with or have forgotten, that you go and spend some time practicing them outside of homework. I also encourage you later this week to come to my integration technique review tutorial that I'll be giving. That'll be specifically focused on integration techniques for BC calculus, if that applies to you, okay? So please, 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 this is going to be a very quick overview of integration techniques. You need to take the time to find the things you need to practice or ask me for them outside of the homework if you're realizing that it is challenging or difficult for you, in particular with improper integrals, because I'm really going to do a very quick overview of improper integrals, okay? The rest of it is on you. Please, please, please be self-disciplined, because I'm only giving one page of examples here, and the rest of it is really practice time for you, because I want to give you a chance to do what you need to do, but you got to promise me that you're going to be self-disciplined about it and take the time to do the things you need to. Please, please, please. All right? Let's go ahead and get started. There's a series of different integration techniques we need to have under our belts. The first of which applies to both AB and BC calculus, is U substitution. U substitution we can usually recognize when we have multiplication. Here we have two things that are multiplied, and the chain rule applies to maybe one of them, and the derivative of that inside looks similar to the derivative over here. So x cubed plus 5. What's the derivative of x cubed plus 5? Well, it's 3x squared, and I see that here. So that's going to be a hint that we got U substitution. Here's how U substitution works again. We choose as the inside function our U value. So I'm going to say that U is going to be x cubed plus 5. I take the derivative of that with respect to x. So that'll give me 3x squared. Then I get dx on one side by itself, because I want to replace everything over here that has x's with u. So I got to find what dx is. I'm going to divide 3 over x squared. So that's going to become 1 over, I'm going to divide 3x squared. That's going to be 1 over 3x squared to the left. Multiply dx to the right. This du, though, is just going to hang out. It hasn't changed anywhere. So I have 1 over 3x squared du equals dx. All right, pretty good. Now for indefinite integration, because we have to be ready for both definite, like this, and indefinite integration, like over here. For definite integration, we do have to worry about endpoints, right? These endpoints represent x values. So I'm actually going to go ahead and change each of those things. So my original x value of my lower boundary of integration was x equals negative 1. Plugging x equals negative 1 into my u value, I get negative 1 cubed plus 5 will give you a u value of 4. Plugging in x equals 1, that's my upper boundary, into my u equation over here, I get 1 cubed, which is 1 plus 5, so I'll give me a u value of 6. So I still go from 4 to 6, so that's a low thing to a higher thing. If they end up switching, it doesn't really matter, because remember when you are using the FTC, it doesn't matter the order of integration, really. So you can just take whatever numbers you get here at face value, and we start substituting in. My lower boundary is now 4. My upper boundary is now 6. 3x squared, I'm going to let hang out. I have the square root of x cubed plus 5, that's my u value. I know dx is 1 over 3x squared du. My 3x squareds will divide away. I get the integral from 4 to 6. Square root of u, I'm just going to rewrite as 1 to the half, because I know I need the antiderivative, and that'll be easier, and du is left. Now I follow all my normal antiderivative things and plug in my endpoints. Antiderivative of u to the half power will be u to the, I'm going to add 1, so it'll be 3 halves power. Then I divide by 3 halves, so I divide by 3 halves. Dividing by 3 halves, same thing as multiplying by the reciprocal, so 2/3. And then I will evaluate from 6 to 4. This will give me 2/3 times 6 to the 3 halves minus 2/3 times 4 to the 3/2 power. And then you can go ahead and simplify and evaluate from there if you want to. But for now, just to keep things moving forward, we're actually just going to leave things like that. We're not going to go any farther. We're just going to leave our work like that. So there's a good example of u substitution if we have definite integral endpoints. I'm going to talk a little bit more about why that, well, probably exactly like this, isn't necessarily like a great representation of what we might see this year. But for now, we're going to leave it like that, okay? All right. Take a minute to digest that. I'm also just like checking my work, make sure I didn't make a mistake there. Okay. Cool. So let's take a look at integration by parts. If you're doing the AB calculus test this year, you actually don't need to continue with these next three. You will need to look at the one at the bottom below us. So skip through the video past integration by parts, integration by partial fraction decomposition, and improper integrals, and meet me down below. Okay? All right. So integration by parts. Integration by parts. For this, we need to remember a specific formula. And if we remember it, it actually leads us through basically everything we'll need to remember, okay? And the integration by parts formula looks like this. Integration by parts tells us that if we're trying to take the integral, I'm going to leave it as indefinite right now. We're trying to take the integral of u, something we'll call u, dv, it is going to be equal to uv minus the integral of v du. Okay? We have to remember this pattern. Essentially, what we're starting off here is with the u dv. So we need to identify what our u and our dv is. Okay? We start off, what is u in this place we're given over here, and what is dv? Now, there are some rules to kind of guide us on this. A lot of people will talk about how do we select u and say liate. We start with logs as our first choice for u. Then we look at inverses for our u choice if we have an inverse there. Then we look at algebraic things. That's like linear stuff, cubic stuff. Liate. Then we look at trig stuff as a possible choice for u. And then lastly, only as a last resort, do we choose exponential things as our u value. So looking over here, I have x, that's algebraic, times e to the negative x. That right there, right, is exponential. So for my u value, I'm going to choose my algebraic thing because it's higher up my list. My algebraic is going to be my u, so x is going to be u. That means dv is going to be e to the negative x. I also need their corresponding either differentials or antiderivatives because I have u. I also will need du, right? And I'll also need v. Right, so what's du? So if I take the derivative of u with respect to x, I'll get du dx equals 1, so du equals dx. If you want, you can just say derivative of u and then derivative of x, if that kind of helps your mind there. We get the differentials, there we go. And then dv, I need to go back to v. So I actually need the antiderivative of this thing here to go from dv. I need the antiderivative with respect to x. So the antiderivative of e to the whatever is e to the whatever, but notice there's a negative x on the inside, so I'm taking the antiderivative. I have to divide by the derivative of the inside. That's always our rule. Divide by the derivative of the inside. Derivative of the inside is -1, so I'm going to divide by -1. So there's my antiderivative. Now I have all the parts that I need, and I can simply say the integral of x e to the negative x dx is going to be, follow the pattern, uv, so that'll be negative x e to the negative x. I went ahead and combine the negative sign and put it in front. So u times v minus the integral of v, which is negative e to the negative x du, which is just dx. The whole point of this is that hopefully this integral becomes easier to evaluate by hand, okay? If it doesn't, maybe we have to use u substitution again, or integration by parts again or something. This one is not too bad now, right? In fact, I can bring that negative sign out in front before I do anything else either, if you don't like doing with all negative signs. I'm going to pull that negative sign out in front, that'll be plus the integral from e to the negative x dx. All right, this becomes negative x e to the negative x. and I need the antiderivative of e to the negative x. Well, we've already done that, right? The antiderivative of e to the negative x is e to the negative x, but then divide by the derivative of the inside, so it's going to be negative. So I get negative x e to the negative x minus e to the negative x as my full indefinite integral. So I do plus c. I guess I should go ahead and add that up here since I have done some indefinite integrals already. Don't forget your plus c for your indefinite integrals. There we go. There's our integration by parts. All right, so what do we do from there? Let's go ahead and move on to integration by partial fraction decomposition, okay? So for our next technique, which is also a BC level technique, we need to remember a couple things. This one we actually have some writing we generally need to do, okay? And for our partial fraction decomposition, there's kind of one big idea to keep in mind, but a lot of them do end up kind of looking the same way in the end, okay? Give me a second. Okay, cool. All right, so in this situation, we want to take the integral of what looks like a fairly complex situation. I guess I should say, for integration by parts, we can often recognize integration by parts if we have a product, but a product where if we took the derivative of the inside of something, it won't cancel out with what we see over here. The derivative of negative x, that's the inside of e to negative x, is negative 1, so it won't cancel out with this x, but it would cancel out u substitution. For integration by partial fraction decomposition, we do need to see a fraction, and a fraction where the denominator here is factorable is usually our sort of go-to key here. So first I like to actually start by just factoring the denominator, 0 to 1 of x minus 1 over x squared plus 3x plus 2. That'll factor into x plus 2, x plus 1, okay, dx. There we go. I have factored my denominator. Now I need to decompose this fraction. Basically what I'm saying is, what will this thing turn into if I wrote this out as the sum of two rational functions with binomial denominators? What does that mean? Basically, I want to say if I chop this up into something over x plus 2 and then add it to something over x plus 1, I want to divide it or chop it up into these individual fractions because the antiderivatives of these will give me natural log stuff that's fairly easy to adjust to. Okay, and take the antiderivatives of. So I got to do some work here. Basically, what I'm saying is, what do my numerators need to be that would get me back to x minus 1? The way we do this, if we want to recombine these fractions, I would need to multiply this first one by x plus 1. So if I take a and multiply it by x plus 1, because to combine these back together, I need to multiply, get a common denominator, so x plus 1 over x plus 1. Plus, to get these two fractions back together, I need to multiply the second term by x plus 2 over x plus 2. So I'm going to call it b times x plus 2. I need to find, hey, what's going to get me back together when I add these back together? What's going to take me back to my original numerator, which was x minus 1? How do I do this? I find the zeros and I start with them. So what happens when x is negative 1? Well, when x is negative 1, this first term goes to 0. Negative 1 plus 1 will give me 0. My next term, negative 1 plus 2, that'll give me 1. So that's b times 1 equals, when x is negative 1, that'll be negative 2. So I now know that b is going to be negative 2. Okay. Then I plug in my other 0. When x is negative 2, what's going to happen? When x is negative 2, I'm going to lose this. It's going to go to 0. I want to get a times negative 1. Negative 2 plus 1 is negative 1 equals, when I come over here, negative 2 minus 1, that'll give me negative 3. So I'm going to get a equals 3. Okay? So I now know what my numerators are. So I got to go back in. Now and check, or now substitute it back in and be ready for my antiderivative, okay? So going back to my integral up here, this is going to be the integral from 0 to 1 of, I plug in what I know for a, which was 3, over x plus 2, plus, I now know b is negative 2, so I'm actually not even going to call it plus. Let me just call it minus 2 over x plus 1, because the minus 2, I'm going to let that minus in front, dx. All right. The whole point of the partial fraction decomposition is hopefully this is actually a little easier to take care of. So let's give it a shot. We need the antiderivative of each of these terms. The antiderivative of 3 over x plus 2. Well, I can kind of factor out the 3. That would give me 1 over x plus 2. The antiderivative of 1 over x plus 2 is natural log of the absolute value of x plus 2. Please don't forget the absolute value signs. Minus, kind of pull that 2 out in front. 2, that'll leave me a 1 over x plus 1. What's the antiderivative of 1 over x plus 1? It's the natural log of the absolute value of x plus 1. All right. I've done my antiderivatives. I now need to go ahead and evaluate at 0 and 1. Okay. So I'm going to plug in, let me start with 1. That's going to give me 3 times the natural log of, when I plug in 1, 3 times the natural log of 3, minus 2 times the natural log of 2, minus what I get when I plug in 0. So that's going to be 3 natural log of 2, minus 2 natural log of 1. And I am going to simplify this because we do need to be on the lookout for certain ways to simplify things using our log rules, okay? Let me go ahead and fix that. Okay. So I'm going to fix this. So let's see what's going to go on here. Natural log of 1, that's 0. So what do I get here? I actually get 3 natural log of 3 minus 2 natural log of 2 minus 3 natural log of 2. Using properties of exponents, I know coefficients I can bring up as powers. Into my arguments. So that would be natural log of 3 cubed, which is 27, right? 27 minus, bring up 2, that'd be natural log of 4, minus natural log of 2 cubed is 8. We got some other things that we can do. Maybe the best way to do this is kind of do it one piece at a time. Subtracting logs of the same argument means we can divide them. So this would be 27 divided by 4, but then I would divide again by 8. So this would be the natural log of 27 divided by 4 and divided by 8. So 4 times 8 is 32. That would be the whole simplified form. Okay. There's partial fraction decomposition. Let's take a look at our improper integrals now. Okay. So an improper integral, there's kind of two forms. What we're going to look at today is if there is an infinite limit of integration. And the first thing we need to do is to actually rewrite that as a limit, because we can't plug in infinity. So we have to rewrite infinite things as limits. So let's call this the limit as c approaches infinity of the integral from 0 to c of 1 over x squared plus 1 dx. Once you've gotten rid of that infinite thing, that's always the first step, then we have to go into what our antiderivative is going to be. We use any of our antiderivative techniques we know. U substitution, partial fraction decomposition, integration by parts, things like that. Well, this isn't a product, so this can't be integration by parts. U substitution doesn't look particularly helpful here because the derivative of x squared is going to give us 2x. It's not going to cancel out with anything. We also can't factor the denominator. So this one is actually just an antiderivative we need to remember, and one that kind of stumped some people on the practice FRQ exam. The antiderivative of 1 over x squared plus 1 dx is arctangent or tangent inverse of x. What to be on the lookout for. Okay? So what does this actually mean for us? This is then, I'm going to keep the limit in front. The limit as c approaches infinity of the antiderivative of 1 over x squared plus 1 we just said was arctangent, or tangent inverse, arctangent of x, all right, evaluated from, I'm still going to call it 0 and c. 0, and c. So what does this mean? I'm going to now plug in c. So that's going to, I'm going to just let the limit hang out in front. That'd be arctangent of c minus the arctangent of 0. And always the endpoint for these kind of improper integrals is now to ask yourself, well, what happens as c goes to infinity? What happens as c goes to infinity? Now, if you've forgotten this, we can actually do a quick little investigation. Okay, I'm going to pull up real quick. Oh, my D&D. I want to pull up Desmos real quick, and let's actually just take a look at the graph of arctangent of x, and just see what happens as the input value goes to infinity. Okay, sorry about this. All right. So if we type in arctangent of x, let's take a look. Well, the arctangent, we need the arctangent of 0. Let's see what the arctangent of 0 is. Well, it's 0, right? Because the arctangent is asking us what angle has a tangent of 0. And the angle that has a tangent of 0 is 0. So that one's fine. But what happens as c goes to infinity, as our x value gets bigger and bigger, the input value gets bigger and bigger and bigger? It looks like there's a horizontal tangent line here. And the horizontal tangent line is, if I graph, is at y equals pi over 2. All right. So what happens as on our arctangent graph then, as c goes to infinity, as the input goes to infinity, as that gets bigger and bigger, our graph of arctangent goes to pi over 2. Because on our unit circle, as you kind of go up towards pi over 2, sine divided by cosine gets infinitely big. All right. That's probably a good one to remember as well. If you're having trouble with that, let me know and we can talk more about it. So arctangent of c, we just saw as c goes to infinity, this thing actually goes closer and closer to pi over 2. All right. Arctangent has a horizontal tangent at pi over 2. Minus the arctangent of 0. What angle has a tangent of 0? We said it was 0. So this goes to pi over 2. All right. Improper integrals can be tricky, which is why I want you, if you're having trouble with that, I want you to contact me and we can work more on it. This might be one to really buckle down on. There's another type of improper integral, one where there's an infinite discontinuity on the interval. We're not seeing any of those today, but we will later. So please start studying this stuff. Go back and review. Look up videos when you need to. All right. One last comment. Now, this year's AP exam is like calculator you can use. It's open notes. They're designing it so that you have to apply a lot of your knowledge and you can't just type stuff in and look stuff up really quickly. So an integral like this, the integration by parts, is something your calculator can do. Something like this U substitution, because it's definite, is something your calculator can do. So we need to be ready for kinds of problems that you just can't plug in on a calculator or look up quickly. Writing out indefinite integrals or improper integrals or questions about these skills that don't involve just integrals you can type in that are definite integrals and things like that. It's one reason why I think you should be very ready for improper integrals, as a heads up. All right. But let me give you an example of a kind of problem that you can't really plug in on the calculator. You actually need to show work for. So it says that k of 1 is 2, k of 3 is 0, g of 2 is 3, and g of 0 is 1. Give us a bunch of different things there. All right. If that's all true, find the value of 1 to 3 of g prime of k of x, k prime of x. Now, this doesn't look like partial fraction decomposition. Does not look like an indefinite integral. So it's either integration by parts or U substitution. But I think it's U substitution because I see an inside, and the derivative of that inside is out here. So let me just treat this like a U substitution and trust the system. That means U, my inside function, is going to be k of x. That means du dx is going to be k prime of x. That means 1 over k prime of x. Du is dx. But what about my endpoints? Because this is a definite integral. What about my endpoints? Well, when x is 1, what is my u going to be? It's going to be k of 1. What is k of 1? Oh, it's over here. K of 1 is 2. Okay, so that's my u value now for my lower boundary. What about my upper boundary, 3? Well, when x is 3, plug 3 into u, that'd be k of 3. What's k of 3? K of 3 is 0. That's my u value. So I'm going to come over here. I'm going to start rewriting my integral. I now know my lower boundary, which was 1, is now going to be 2. My upper boundary, which was 3, is now going to be 0. You don't have to worry about those. Just leave them as is. I now know that g prime k of x is u, so that's g prime of u. K prime of x dx I now know is 1 over k prime of x du. Look, my k primes will cancel out. And I get left with 2 to 0 of g prime of u du. What's the antiderivative of g prime of u? Oh, it is just g, right? That's what the fundamental theorem of calculus says. G of u evaluated from 2 to 0. So this is going to be, I'm going to plug in 0, g of 0 minus g of 2. What is g of 0? G of 0 is 1 minus g of 2 is 3. So this integral has a value of negative 2. These kinds of questions that are in function notation, or you can't just plug into a calculator, you actually have to do some work with and deeply understand the concept you're working with here, u substitution, is what we need to be on the lookout for, okay? Taking time to practice and really know each of these techniques is important so that you can apply them in these situations that are sort of decontextualized or in function notation, things like that, all right? So that's it for today. What I want you to do is this, all right? If you are if you're going to be taking just the AB test, what you need to do is do just this first free response question, okay? If you're taking the BC test, you need to do the first free response question and the second one. In either case, as usual, score yourself, grade, make corrections, do the score report. You also need to take the time to do each of the 4 concepts that I've assigned if you're in BC. If you're in AB, it's just 1. Okay. And I am looking for you to get to 75%. This is to have you take the time to practice with this. I've made this video shorter, so you'll take the time to practice with each of these techniques and get better at it. If you need to watch the videos, contact me. You need to take the time to really get a better hold of these things. YouTube's a great resource for looking up how to do these things as well and seeing examples, okay? All right. Please go ahead and make sure you take care of that and drop by my integration techniques for BC Calculus tutorial later this week if you are looking for another chance to practice and get some more questions answered. All right. Love you guys. Talk to you later. Bye.